Somos tu segundo hogar y mantenemos la excelencia académica como la bandera que nos caracteriza con un ambiente cálido y humano pensando en ti. Permanezcamos unidos y seamos fuertes en el camino. Cuenta con nosotros para mejorar tu futuro. Universidad Internacional UISEK, personalización en serio.
Muy buenos días con todas y con todos. La Universidad Internacional UISEK les da la más cordial bienvenida al Lecture Series versión 3, Fabricación de Robótica, que tiene como objetivo evidenciar los procesos de investigación, de innovación tecnológica en el campo de la arquitectura y de la ingeniería civil. Este Lecture Series es organizado por la Facultad de Arquitectura e Ingeniería Civil de la Universidad Internacional UISEK y queremos darles la más cordial bienvenida a nuestra ponente, a nuestro decano, al público que nos acompaña el día de hoy. Sin más, quiero darle la bienvenida a nuestro decano de Arquitectura e Ingeniería Civil, Néstor Yorca. Bienvenido, Néstor, muchas gracias.
Muchas gracias, buenos días a todos, buenas tardes a los que nos ven desde otros lados. Les quiero agradecer a todos por su presentación, por su participación, pero sobre todo a Catherine por estar con nosotros. Les voy a dar un saludo pequeñito y explicar un poco las razones por las que le hemos invitado a ella. En la Escuela de Arquitectura de la Universidad llevamos ya algún tiempo buscando nuevas maneras de introducir estrategias de proyecto, de herramientas que fomenten nuevos modelos de construcción, de gestión, de aplicación tecnológica, pero sobre todo de un concepto que denominamos pensamiento prospectivo, es decir, cómo los arquitectos o los ingenieros civiles que estudian ahora tienen que ser conscientes de que están diseñando para un futuro que todavía no controlan y cuáles son las herramientas que puede pasar o que pueden tener para hacer más lógico y más consecuente esta participación en la ciudad. En un momento en el que la arquitectura se enfrenta a nuevas exigencias que le den balance a la afectación que hacemos al planeta y a las necesidades de una sociedad que cada vez requiere más recursos, debemos utilizar el ingenio y la visión del futuro como soluciones. Buscamos caminos que otorguen nuevas capacidades al espacio, desde las categorías clásicas de nuestra disciplina, la actividad, la forma o la utilidad, y la tecnología como un medio, como una herramienta para esto. Y para buscar, o en la continuación de esta búsqueda, hemos invitado a Catherine, que van a escuchar ustedes ahora, mucho que decirnos y una alta capacidad para poder hacer este salto sobre este nuevo paradigma. Es profesora de la Universidad de Múnich y voy a dejar ahora que le introduzca el profesor Marcelo Táñez para poder darle la bienvenida de nuevo. Muchas gracias a todos y de nuevo gracias, Catherine, a ti por estar con nosotros.
Buenos días con todos, todos los asistentes. Quisiera presentar a Catherine Dorfler. Ella básicamente tiene una gran experiencia en el tema de la fabricación a nivel digital y en sitio. Si bien nosotros hemos conversado con varios de ustedes, varios estudiantes que están aquí presentes, tanto de la Facultad de Ingeniería, de la Facultad de Arquitectura, y también un poco de estudiantes de lo que fue la maestría en arquitectura. El ideal de esto es que, si bien nosotros hemos visto muchos temas a nivel digital, ¿sí? Catherine tiene una gran cantidad de proyectos en los cuales lo da implementado en sitio, y ustedes tienen varias preguntas sobre esto, si bien me las han hecho a mí. En este caso no tenemos todavía la experiencia ni la capacidad tecnológica de implementarlo, si bien tenemos un laboratorio que muchos de ustedes ahora lo conocen, en aras de que la investigación esté ligada hacia ese objetivo. Entonces quiero que Catherine nos muestre la gran cantidad de proyectos que tiene, cómo se llega a implementar un robot en la construcción, que es la gran pregunta que todos ustedes tienen. Y si bien tenemos preguntas de costos, también debemos de entender que hay mucha investigación por detrás, hay muchos proyectos de inversión y que no va a ser algo tan real a corto plazo, pero ya vemos proyectos que se han ejecutado en tiempos actuales y vamos a ver hacia dónde va la investigación. Entonces quisiera dar paso a Catherine y muchas gracias por estar aquí con nosotros.
Yeah, thank you very much. Thank you for the introduction. Thank you for the invitation. I will start with sharing my screen with you. Give me a second. Oh, sorry. And you should now be able to see my screen as well. Maybe you can give me a quick feedback if if that is the case.
Yes, Catherine, we can see. Thank you very much,
Okay.
Catherine.
Then I'll start. Hi everybody, and a very warm welcome to my talk, and thanks again for the invitation. I'm going to talk about today about human in the loop, how machine collaboration, human-machine collaboration could shape the future of digital design and fabrication. As already said, my name is Catherine. I am a professor for digital fabrication at TU Munich. And I have a small research group in that field. I will start with a short compilation, a video compilation of a few projects that I have been doing during my PhD period at Grammatikola Research at ETH Zurich, in which we tried developing autonomous processes for robots, not in the lab, but as already mentioned, out at the building site. So what we tried here was to bring robots out from the lab directly on building sites, and we did this in various processes with various technologies, with various different building processes. And all of these videos have one thing in common, something that we have not been really focused on, but in retrospect is kind of important to recognize. And what they have in common is not the robotic part, but concerns basically the people, which you see popping in and out in the videos. So I like to show these videos 2 times just to make to make it more apparent that in retrospect, when looking at these projects, one of the main questions that keeps appearing upon reflection is the following: if the manual material feeding and the robotic material placement is the ideal task distribution between humans and machines, or if we can do somewhat better. And the question which keeps coming back into the work of my group is the question about which benefits could be created by actively and intentionally embedding human cognitive skills into digital design and fabrication processes, and vice versa, which benefits could be created by actively and intentionally embedding human, by augmenting human decision-making processes with machine intelligence, and also at which stage of the digital design to fabrication axis, in which the design end of the axis is related to the virtual aspects, including topics in decision-making, information representation, exchange, communication, and the fabrication concerns the physical processes, including but not limited to material processing, localization, navigation, tolerances, robot kinematics, and also the physical interactions between humans and robots. So when we look at today's machines, they are not purely mechanical, but they are reprogrammable digitally. They can be connected with sensors and smart control algorithms, which ultimately radically expands their flexibility and their space for application. So if we want a hybrid human-robot team or a hybrid human-machine future and realize the vision of a collaboration between humans and machines, we think that the trick is to get humans and machines speaking to each other. So this is already more than 10 years back, where my colleague Romana Rust, so a long-term colleague and collaborator of mine, were playing around in the architecture and faculty's digital fabrication workshop, where we got this robot manipulator, and we were both caught by sort of a fascination for these robots, but not as a tool for automation, but rather as an extension of the person's hand. So this was one of the first tests that we did. We used the iPad's orientation sensor to control the orientation of the robot's end effector in real time. And back then we started to envision the robot as a co-worker and an extension of a person, and in constant interaction, speaking to each other. To explore questions along these lines, we, in a very early project, it was actually a master thesis, we developed a system which we named SANS, for Sensor and Actuator Network, for SAW, which we thought is like no borders, very naive, I'm aware. But we envisioned basically a system where people and robots could be connected via various sensors, like a camera, iPad, or 3D digitizer, bringing information from the physical world to the digital model, and to establish a possibility for humans to interactively take part in a fabrication process by enabling designing during fabrication and influencing and moderating digital fabrication processes while they are progressing. So we established the communication between these different sensors and also the robot as an actuator, and we implemented a server-client application, which we were writing in a very crude way in Python. And it was basically a requirement to implement a very open and extendable system, which would be easily adaptable to any sort of device. And in this application, we had a server which delegated data exchange between different sensors and actuators, and would also incorporate a model with different algorithms for moderating a fabrication process. We thought that this implementation was something very novel, but after a few years, we found out that this already exists in a way more mature form and developed all over the globe, which is basically the concept of which some of you are familiar with, which is called ROS, the Robot Operating System. However, our very rudimentary implementation at that time allowed us to connect any sensor input with various CNC machines or robot manipulators with a few modifications. And in this video, you can see a very first test in which we tried the simultaneous milling of a 3D digitized surface, where a person is actually scanning a differentiated surface, and a 3-axis milling machine is milling out the digitized surface at the same time. And what you can see here is that the scanning of the surface is a complete manual process. Therefore, the milling result is not a perfect copy, but it has these imperfections of the hand movements inscribed in the surface of the object. Going a bit further, we started to explore this notion of real-time control and interactive fabrication by using various sensor feedback. And we explored algorithms which are based on sensor input and user interaction, although they are based on very, very simple rules. You can see here how this robot is actually letting a thread fall on the surface, and it would follow an internal algorithm, but a user can intervene in the process and basically direct and sort of change the movement of the robot. You can see when the person is basically intervening by putting the hand on the surface, which is tracked by a camera. So what we effectively try to combine to combine the process of design with the process of making, so that the designs don't have to be frozen before going into digital fabrication process, but that you could develop this during fabrication. And this, of course, was enabled by these various sensor devices, which helped monitoring the current state, where extracted parameters were used for input for the fabrication algorithms, and they also allowed for user interaction without using a dedicated external input device, but also through the direct manipulation of the physical object. One last of these old videos, and I'll jump to the new ones, but I think it's important to get this background information. But we ended up doing a project which we called stick piling, where a robot would pile sticks in a non-predetermined manner. So a user could basically place some sticks on the surface of this table, which then would be tracked by a camera from below the table. And by placing an initial configuration, the user can basically define an initial state. And you could see Ryan Luke Johns, who was placing some sticks at the beginning. And then while the sticks are tracked, an algorithm starts to try to find basically stable configurations in starting to piling up the sticks. And you can see here in the background the digital model. And then here the physical counterpart. And when a new stick is placed on the table, this would be detected. Then the algorithm would find a stable position on the already placed pile. And this process can basically go endlessly, and it would only stop if no stable position can be found, or a user can also intervene in this case and remove sticks or place sticks with different lengths, so that the process can continue successfully. So I'm aware that this process are very sort of rudimentary and very playful, but what we tried to do was to kind of open up this kind of determined design to fabrication by kind of creating this open loop processes. So there exists a very loose definition for autonomy for humans or machines, as the extent to which a system can carry out its own processes and operations without external control. And there exists also a more specific definition of autonomy in robotics, so as related to robots, to be the extent to which a robot can sense the environment, can plan based on that environment, and then act upon that environment with the intent of reaching some goal without any external control. And there are two major groups of opinions on autonomous implications in the human-robot interaction context. And the main opinion suggests that a higher autonomy yields to less interaction between humans and robots, in which research aims to maximize system performance with minimal human intervention. So this can be, for instance, seen mostly in the attempts of realizing autonomous driving, where we don't want any human intervention in the autonomous routines of the robot, in this case, a car. So this approach allows to do many things. So it allows to deploy robots not only in very controlled and structured environments, but it also allows us to use robots for fabrication directly on building sites, where mobility, perception, and scene understanding and the integration with a suitable design to fabrication workflow allows robots to cope with uncertainties and unforeseeable events in their environment and with the materials in use. And this approach of basically maximizing system performance with minimal human intervention was also something that I pursued mainly in the area of my PhD at ETH, where I basically dealt with this topic of bringing robots on site. And where this approach allowed us to realize projects such as mesh mold and in situ fabricator, which I will explain in a bit more detail. This process, this robotic in situ process, applies a novel construction system for reinforced concrete structures with the name mesh mold. And this is a process in which a dense steel rebar mesh is fabricated, which acts as formwork for the filling of concrete and as reinforcement after the concrete is hardening. And this fabrication technology was specifically chosen to show the full potential of robotic in situ fabrication. First, because it is fully load bearing, and the process facilitates the construction of geometrically differentiated and structurally informed monolithic structures in a material, but also a labor efficient way. This process was demonstrated as part of the residential unit called DFAB House in a research environment at the material testing facility of Zurich, in which this bespoke reinforced concrete wall, which is highlighted here in red, is providing the main load-bearing element of this unit to carry this cantilevering floor and to carry the two-story timber unit on top. So we developed a robotic end effector that can primarily assemble this free-form rebar mesh through bending, cutting, and welding. But this end effector also integrates a bunch of sensors. Here, a vision system, one for the robot's localization on site, and then a second one for surveying the fabrication and to cope with uncertainties on the way. So we developed a design tool for architects that allowed designers to create wall designs that are informed by fabrication-related constraints. The design tool allows the geometry of a wall to be locally undulated to increase the stiffness of the wall, with the goal to decrease the thickness and to produce the most slender geometry possible, given the load conditions of the upper two floors. And the model, of course, also includes all the fabrication information. This mesh is in contrast to the layer-wise 3D printing that you maybe know from 3D printing. In horizontal layers, this goes vertically, such that the mesh fabrication expands in the direction of the movement of the robot, which allowed to fabricate this mesh from 8 subsequent robot locations, in which at each location the the robot had to be relocalized, which is done with this camera system looking at fiducial markers mounted at the base of the foundation, and by the second camera system, which is looking at the mesh directly, allowing the mesh contour to be sensed, registered, and then also to compensate locally for fabrication errors. So, for instance, the local deflections of the mesh, which occurred due to inner forces in the mesh fabrication, and also slight inaccuracies in the robot's localization. And this feedback loop allowed the deflection of the mesh contour to be iteratively measured. You can see here the colored lines are the deflections measured, and the black lines are the actual as planned locations where the fabrication data was then adjusted accordingly. This documentation shows the process from the movement of deploying such a mobile robot on site. You could see how it was transported with a container onto the platform where the house was built. It had to be housed because of weather protection. And here you can see the sensing system, which is tracking the fiducial markers at the foundations, such that the robot would recognize its location on site. And the welding process of the mesh, which is really like 3D printing, but just in a very loose way. And then the camera system, which would iteratively measure the mesh itself in order to be set to compensate for any deflections that occurred as the fabrication went on. So then the fabricated mesh is filled up by pressing the concrete in from the side and traveling the outside, and then also creating the smooth surface where you can see that the construction actually really doesn't need a formwork and can be a fully load-bearing system. Now, the accuracy of this fabrication process was validated by taking some ground truth measurements after the fabrication was finished. And we could prove that the deviations of the fabricated structure stayed well within plus minus 1.5 centimeters in comparison with the as planned CAD model. But more than that, the process was fully autonomous and could be fabricated without causing collisions or without having being reliant on any interventions. This then allowed this prefabricated concrete slab called the Smart Slab of the Digital Building Technologies Lab to be installed in place on top of the wall without any adjustments. The wall thickness was, as said, only 12 centimeter in cross section, which is very slender, and then was also taking the loads from the two-story timber unit, which was placed on top. And covered with this translucent insulating waterproof pillow foil to finalize the unit. So while this project was a very unique chance to prove that in situ fabrication is not only a future vision, but that it is actually ready to be applied successfully in a real-world construction project, it has also been largely criticized that existing approaches to robotization usually aim at the complete substitution of human labor. And when you now remember what I said at the very start of the talk, there's a very interesting perspective in the field of human-robot interaction that suggests that if you create highly autonomous system, that there's a positive correlation between autonomy and collaboration. So that only with very high levels of autonomy of robotic systems, a balanced partnership can also be established, where humans and robots can work together on common goals with proper communication and complementing skills, allowing to explore and balance the level of autonomy and collaboration between all participating agents, whether or not this concerns. Okay, now I think my PowerPoint crashed. I'm quickly gonna restart. Could you follow me until here?
Yeah.
Don't worry, Catherine.
Yeah.
Thank you.
I should be right back. Yeah. Okay. No, I just need to reshare my screen. Okay.
Yes, right now we can see. Thank you very much.
Okay, perfect. So with a higher level of autonomy in robots and machines, we can actually start to explore and level and balance the interaction and the collaboration between participating agents, whether this concerns people or robots. So we turned to a completely different project after having basically realized this concept. We turned to a more human-centered perspective, and we pursued an approach in the field of digital fabrication by hybridizing machine intelligence with traditional manual construction techniques, and which has been shown in the project Augmented Brickwork, my latest project in collaboration with Grammatica Research as well. We departed from the robotically fabricated brick facade of the Ganten Winery in Switzerland, which was built in 2011 by industrial robots, and we took this project as a major source of inspiration. But instead of fabricating such a geometric differentiated wall robotically, augmented brickwork is moving away from robotic manipulation towards manual operation, in which craftspeople are guided by intelligent augmented reality tools to gain robotic precision. So for this, we actually took the sensing system off the mobile robot. Actually, Timothy Sandy, who by now has founded a startup called Incon AI, so Instruct Construct. He's a robotic scientist and a long-term colleague of mine. He developed a technology which allows to track discrete objects with a known geometry in space with very high precision. And instead of using it to control mobile robots, as you've seen before, this is used to instruct, to superimpose instructions on a video feed and to instruct humans to build complex shapes with high precision. I'm just going to play this video quickly so that you understand the concept.
In this sequence, a simple brick wall is built using the tracking system to guide the placement of the bricks. The desired geometry of the structure and the building sequence are pre-programmed into the system. When the user is ready to place a new object, the desired position of that object is projected in red into the images. Because of the accuracy and smoothness of the tracking estimates, This provides an intuitive reference to guide the user.
So we investigated this technology for the traditional craft of bricklaying by translating certain or very specific crafts principles, such as, for example, knocking this brick into the mortar, to translate this into interactive visual instructions for guiding this knocking behavior. And we upscaled the technology for the construction of a brick facade, also for a winery, but this time not in Switzerland, but in Greece. Also here summarized in a video. You can see here the finished wall from the inside. And you can see here the bricklayer putting the mortar and placing the brick, knocking it in slightly, and then the brick as it is tracked in real time, and the arrows which indicate the locations as to where the brick has to be knocked into the correct location. And basically the length of the arrow indicates the strength of knocking. Yeah. We intended this to be a one-person routine, but we ended up with actually having to have two people working in parallel. So one person which is putting the mortar and placing the brick, and the second person which is measuring the digital model of the facade. And then the kind of the finished facade from the outside. You can see here how we created sort of this shadow effect by varying the rotation of the brick, and also how this, basically changes during the day depending on the location of the solar radiation. Also, the layers of the bricks are not horizontal, but they are curved, so to increase this sort of flowing appearance. So I have been teaching now at TU Munich for 1.5 years, and the first project that we started here in continuation of this idea of collaborative workflows, so we developed a project called Prototype as Artifact. It is a work by my PhD student Lidia Atanasova, who investigates new collaborative workflows between humans and robots to combine explicit machine intelligence with implicit human knowledge and creativity. Again here, thanks to novel augmented reality technologies, two users and a robot collaborate in the assembly of a complex wooden structure in alternating physical actions. So the spatial timber assembly, which you can see here in this image, is being constructed by following a predefined rules or assembly grammar, as we call it, but is not planned at the beginning of the process, but its configuration is instead designed during fabrication. Again, exploring and trying to figure out this notion of a linear or of questioning the linear digital design of fabrication workflows by carefully looking at craft principles, such as shown here in this video, named the column pattern making, which was extensively described by a researcher named Terry Knight, which are based on a set of rules, but which are open and can change and be adapted during the process. For example, to pursue new ideas or to take errors into account, or to address some sort of material properties on the way. Where making is not just doing, but is doing and sensing, and where the linearity of the workflow can be redefined into this sort of circular manner. For this, we have designed an assembly grammar, which describes basically rules for temporal processes. In this assembly grammar, elements are grouped into modules of 3, and the first element can always be placed freely by a user. And then this freely placed element is digitized, basically tracked by the augmented reality system, and is then completed by a robot which places the subsequent 2 elements to create this grid-like structure. And again, I'm showing a video. So the sequencer set starts by user placing the element freely at any desired location. And then this physical action has to be digitized. For this, the user points the phone towards the structure, approximately at the right location so that the tracking can be initialized. And at this point, you can see the overlay of the digital model on the physical structure. It basically snapped to it by being registered correctly. And once the structure is registered correctly, the newly placed element has to be also registered. Yeah, here you can see how the user basically can move the phone around freely, and how the user can also look at the information overlay. In this case, these kind of outlines and also the arrows. The arrows actually indicate possible continuation points of the structure. And now the newly placed element, which has been placed before, is now also registered by the app. So now the user has to click Add Object to add a new object to the scene. And it can also position it approximately at the right location. And at this moment, also the tracking can be started. And then the exact location of the tracked element is fed back to the digital environment. So now the registered pose of the newly placed element, as shown in red, is the base for the 2 new elements that are placed robotically. And you can see here the robot, how it is basically simulating the process and then also physically executing it to complete this kind of cross structure. Again, here the person is fixing the element with a screw. And we fabricated this prototype of 102 elements, so on the construction area of 2.3 meters by relocating the robot 3 times. And this is the digital twin of the fabricated structure, in which the red color indicates the elements which are placed manually and the blue ones which are placed robotically, and also the tracking accuracy of the freely placed user elements, which was also observed to be well within ±3 millimeters. This is how this prototype looks like in the end, and as it's an open system, it also can be could be continued if we had continued to build. So as you can see, this process is it's hard. It's hard to digitize physical actions continuously in order to put it into a digital model, and then in order to plan robotic manipulation procedures. You can see here that this process was done really stepwise. So doing something, sensing, registering, digitizing, planning, and then planning robot routines, and then also complementing the manual physical actions by robot physical actions. But we would wish for this process to be all, happening at the same time, but I think we are not there yet. So I will close my talk with the last project, a little bit less technical, a project called Climate Active Bricks, which takes the idea of human-robot collaboration again to the construction site, which is the result of a one-week summer school of our professorship. And in this project, we investigated how climate-active properties of the most simple building material, which is a brick, in the outer shell of buildings can be released through the integration of computer-aided design, climatic simulation, and robotic production. Sealed surfaces of city walls that are directly exposed to the sun tend to radiate. You probably know this in cities which are heating up in summer. And they radiate the received heat and create heat stress for city dwellers. And the reduction in the solar radiation of such facades, for example, through self-shading effects, could help to reduce the radiated heat and improve the local microclimate for residents in the outdoor urban environment. So we have selected a location in the city of Munich, a southwest facade that is heavily exposed to solar radiation as a location for planning and constructing a prototype of this approach, with which we could test and also verify this concept. For the design, we wanted to expand the concept of integrated architectural functions in the exterior area of building envelopes, shown here on a very historic example by Leon Battista Alberti, in which the social impact of architecture and awareness of an urban space can be seen in the articulation of the facade. You can see here that we have here a bench integrated, and also it is basically organized in different zones. We developed the design of the facade prototype on the basis of a red trap bond masonry composite in which 4 bricks are arranged in a rectangle and laid in a hitched manner, creating a cavity in between. And in this red trap bond, we use 40% less mortar and 20% less bricks as to a conventional brick masonry. And in addition, we can, it allows the front of the brick to be translated, but also rotated in order to create a self-shading effect. So we used simulation tools in where we analyze various variations that affect the solar radiation of brick constellations. So without modification, you can see here how the full facade is exposed to the solar radiation, and by translating them to the back and then rotating them, falling out in relation to the sunlight, the value of the absorbed radiation can be reduced, which also leads to a reduction of the radiation and the heat load. We then took the collaborative robot that can work hand in hand with people to the site to jointly lay the masonry, in which the precise laying of the stones, in which each individual position is precisely defined by the digital model, was carried out by the robot, and the mixing and laying of mortar and the grouting, a process which requires great manual skill and adaptation to external conditions, was carried out by the students with whom we built up this wall, and enabled sort of an intuitive workflow between the precision of the robot and the skill and the craft of the people involved. Here we didn't use any kind of automated sensor system to basically just measured in the robot by hand by measuring point coordinates, which allowed to, on a very analog way, to relocate the robot during construction. And again here, summed up in the video, which is the last.
In the context of climate change and especially of sealed surface in very dense urban environments, microclimates are a very sensitive, important aspect of our well-being.
It's already well accepted that the cities are shaping the microclimate, and the microclimate is shaping how people are using and experiencing the cities and the urban environments. One of the effective methods to encourage people to use the public space is to give them comfort opportunities, meaning to create cold spots in the city to recover from the heat stress. This can be done either by planting trees or creating surfaces with minimized solar exposure.
Sometimes we cannot increase the greenery of our cities, so we need to lower surface temperature of our urban walls. We do this by adding a shadow surface, so we can lower the surface temperatures by creating shaded walls of our buildings.
The project Climate Active Bricks is about combining the research field of improving urban microclimate and the field of robotic fabrication. Robotic fabrication allows us to directly fabricate from a digital model. So the geometries that we generate by utilizing simulation tools can directly be fabricated one-to-one by a robotic arm.
The Climate Active Bricks project is a good example of an experiment enabled by digital tools through the entire design process, from conceptualization to the fabrication.
So with this project, we also tried to combine human craftsmanship and robotic fabrication. We actually use the robotic manipulator only for the precise laying of the brick, whereas other tasks like putting the mortar or mixing the mortar, that we would combine with the students' works. When we perform the simulation, the goal is to reach the minimum solar exposure. That means that the geometry of the brick wall results in a geometry where each brick has an individual location. So it would be very difficult for a human to build this wall. So in this case, we exploit robotic fabrication because it allows us to directly take the result of the simulation and fabricate it into millimeter accuracy.
We improve the human comfort level by lowering surface temperature in the urban context. So far, we can say that the lowered surface temperature reduces the heat stress on the human body. Normally, our urban walls are very flat surfaces. So what we do by creating a staggering pattern of brick walls, we generate self-shadowing effects in the wall that allows to reduce the surface temperature of that wall.
Promoting people to use the public realm is highly dependent on how walkable, comfortable, and healthy we plan our cities.
Okay. So in conclusion, let me briefly restate a few main points. So while there are many technological challenges ahead, these works and experiments try to formulate an alternative vision of a fully automated building design and robotized construction. Instead, they proclaim the idea of a hybrid and mutually augmented human-robot work team, which could form the basis of a paradigm shift in the field of architecture and digital fabrication, and to create mutual gain. And two, in the future, provide greater flexibility, design freedom, application spaces, and after all, also social sustainability. So, thank you very much. I hope it wasn't too long. I think it was longer than I expected. And I'm happy to receive some questions by you. Thank you very much.
Thank you very much, Catherine, for sharing with us this knowledge and for all your work. And we have so many questions, so I will start with the first one. What are the main challenges for the implementation of robotics processes in construction on a large scale?
That's basically the question that concerns all our research of the whole research field.
I think that maybe with the whole research.
Yeah, exactly. Yeah. So basically this is, I mean, basically the whole research is actually concerning this question. So, and the challenges are multiple, right? There are technological challenges, which I think can be solved more or less, but then there are also challenges on the level of sustainability, which are much harder already. And then there's also challenges for, we call it user acceptance, but acceptance in general, no? So do we want to create these technologies just because we want to know that it works, or do we also want to create something meaningful with it? I guess in the last 10 years, we have solved a lot of technological challenges, but by not considering the result and the impact that it would have. And I think now, after having the period of 10 years of really an explosion in the research field, I think now it's also time to reflect upon what do we actually need, what do we actually want, and what actually makes sense to proceed with.
Perfect. Thank you very much. The second question is, what do you think about the relation between the research processes in academia and the demands in the professional practice of architecture and construction?
Yeah. So there is a high demand from industry to automate and to rationalize construction processes. There's, however, also a gap between the research questions which are tackled in academia and the solutions which can actually be transferred to industry. Because, let's say, in academia, you can very much still be in a sort of protected environment where you can construct the scenarios. However, when you go to industry, the systems must be completely fault tolerant, they must be safe, they must be robust. So I guess the process has only started, processes which are very simple and like 3D printing is a perfect example, will probably be transferred to industry. Not because it's the most smart process, but it's a very robust and simple process.
Thank you very much, Catherine. The third question is, how do you work with the concept of efficiency in your activities in the Robotic Fabrication Lab in Munich? Can you explain a little bit this concept in terms of planning, processes, technologies, time, materials, and robotics?
Yeah. So what we have been mostly targeted on or focused on is the material efficiency. So all the additive manufacturing methods are following this sort of concept of placing material only where it is actually needed. So for instance, to reduce the amount of formwork needed in conventional construction methods, with additive manufacturing, we can place material in free space. And by optimizing the geometry, we can also place it only where it is, for instance, structurally needed or needed for acoustics or building physics requirements.
Perfect.
And then to reduce to the most necessary amount.
Perfect. Thank you very much, Catherine. And the last question is, can you please provide further explanation about how the implementation of robotic processes can create positive effects and in an urban context?
So the last project that I showed maybe will be a project which will be applied in a larger scale, also in the urban context, because it allows to, so digital fabrication in general allows to create bespoke and custom solutions. So in this case, we can design for geo-optimized facade systems, which are optimized for the location where they are placed, and in which bespoke geometry can be produced quite easily. And in this, does this answer the question?
I think so. Thank you very much, Catherine. It was amazing to have you here with SEK International University of Ecuador. We're very happy. We hope to have you here soon in Ecuador. Thank you very much for that. I will give the floor to our Dean, Nestor Yorca, for a final thanks. Thank you.
Thank you very much.
Thank you, Catherine, again. Thank you for everything. I have one question also, because all the things that you are showing us in your lecture has a new role from the humans in the robotic fabrication. So it's like a mixture between the design and also the construction in like real time. So I want to ask you, what are the new knowledge that you have been developed in your prototypes that that makes, if it is better to have humans involving in the process, or only is like a new way to see the fabrication in new steps? So that's the question. That's the question. How do you feel the participation of the humans in this process that is usually not in real time? It's a process not so fast, not so. It's sometimes like a little boring because you have the ideas really fast, but then the implementation is not so fast. So all the mixture that you make eliminates that step. It's more like a thing to design, not only the process.
So thank you for the question. There are two answers to this. So the first one is that, let's say in the last 10 years, we have been trying to, what I was referring to in the first projects, also what I did at ETH, is to fully automate processes and to really, completely rationalize building construction. Also with this idea in mind to have these fully robotized construction sites, or the fully robotized prefabrication, no matter what. And often the people involved in the processes have been cut out of the videos to kind of also transmit this vision or this wish, for this this ability to fully automate processes. And I think we have been realizing that this may first not even be possible. So that's one way. But the other thing, that this may also not even be needed or wanted. So because in fact, if we think realistically, we will always have a combination of the two processes. So some things machines can do better. Like we all know, we have our mobile phone, which we cannot live without. But some things we actually want to keep and we want to operate as a person as well, in cooperation with machines. So what we're now trying to look at is the interfaces between the two, the task distribution between the two, and the seamless and very fluid interaction and communication between the two. So, and as I said, this is technologically also hard, but there's a wish to kind of make this digital physical overlay completely fluid. So to have these both worlds connected, not just on the screen, but in our physical environment, right? And by that, being able to fully redefine and rethink processes between machines, peoples, robots, and so on.
Yeah, thank you again. I think that's one of the biggest achievements of all the condensed work that you have. So I'm gonna give you my opinion in Spanish for all the people in the YouTube, yeah. Pero sí, muchas gracias de nuevo a Catherine, gracias por su presentación. Hay una cosa importante en lo que nos presenta ella, bueno, muchas cosas aparte de la rigurosidad con la que sucede el proceso, es que hay un nuevo rol en el ser humano que se introduce en la fabricación robótica, y probablemente hay una idea que podrían llevar ustedes de toda esta presentación de entender que esta transición entre la fabricación robótica y llamémosle las tecnologías previas a este tipo de herramientas, también tienen un papel muy importante en el ser humano. Son las personas las que pueden crear los vínculos entre las necesidades, entre las capacidades tecnológicas, entre el verdadero requerimiento, digamos, de la construcción y las capacidades que puedan tener desde lo climático, lo constructivo, la sostenibilidad, otro tipo de cosas, en las que el papel del ser humano también es importante. Es decir, esta transición entre la construcción de estos sistemas automatizados y la que hemos visto o la que hemos aprendido en sistemas previos, no es una ruptura, es un puente para poder entender que juntos hay cómo tener mejores resultados. Y thank you again, Catherine, for the lecture, because gracias, Catherine, por tu charla, porque mezcla o da un resultado de cómo los dos papeles, el humano y el tecnológico, pueden contribuir para un mejor resultado. Así que muchas gracias a todas las personas que nos han visto en YouTube. De nuevo, gracias, Catherine. Y nos vemos en la próxima.
Thank you very much.
En los momentos de crisis, tu educación es una oportunidad para crecer, para brillar y superarte ante la adversidad. En la UISEK somos tu segundo hogar y mantenemos la excelencia académica como la bandera que nos caracteriza con un ambiente cálido y humano pensando en ti. Permanezcamos unidos y seamos fuertes en el camino. Cuenta con nosotros para mejorar tu futuro. Universidad Internacional SEK, personalización en serio.